Hello, I'm Mirdad Simkhani, your calculus professor, and this lesson is about integral. First, we talk about integral and its definition. Then at the end, we pose a question. Why do we care? The integral from a to b of a function f with this graph is the algebraic area between the graph and the x-axis. By algebraic area, we mean that the area above the x-axis is considered positive area, and below the x-axis, the area is negative. If the graph is in the shape of a known geometric figure, like semicircle, a trapezoid, and that geometric shape has a formula for its area, we can use that formula to find the integral. More generally, we define the integral as the limit of the Riemann sums. Finding an integral is known as the area problem, which is one of the two main concepts in calculus. The other is the familiar tangent problem. We will see that the area problem is a limit problem, like the tangent problem. We know how to approximate the area by using Riemann sums, like right sum, left sum, midpoint sum, or by choosing any x in any of the subintervals to construct the height of a rectangle. We know how to do that approximately, and as we increase the number of rectangles, we know that the approximation gets closer and closer to the actual area. As we can see here, as we include more and more rectangles, we reduce the error. Now let's symbolize this problem. We use n to indicate the number of rectangles. In this case, n is 6. And delta x denotes the width of each rectangle. So if we divide the total length of the interval from a to b, which is b minus a, by n, that gives us a delta x. So this is a formula for delta x. And then the area of each rectangle we know is the delta x, the width, times the height. The heights are f of x1, f of x2 in this picture, f of x3, because these are the, if you evaluate, for example, f at x2, you get this height, which is the height of that second rectangle. Similarly for all the other x's. And if we factor out delta x, then this expression gives us the area. In general, when n is any number of rectangles, this expression looks like this. We use this notation sigma. This sigma indicates the sum, and we use a variable, an index like I, to vary from 1 to n, n being the number of rectangles again. So by adding all those, we can write that addition as sigma. We only represent each of those by one function evaluation at xi, where xi could be x1, x2, x3, x4, x5, x6, as I changes from 1 to n. In this case, n is 6. So this is a sigma notation that we use to shorten that Riemann sum. And for n equal to 12, this is how the picture looks. And notice that the xi's depend on n, because these nodes are not necessarily going to be the same. And we have more and more of them. So I'm denoting that dependency by using a superscript with n in parentheses. So that's just a matter of mathematically making this make sense more. So this is how we represent the sum of those areas of these rectangles using sigma notation, and we call it a Riemann sum. And as we let n grow, like here n is equal to 24, we get closer and closer to the actual area. And in this, you can see already that this is a limit problem. We are letting n to tend to infinity. And therefore, we can represent that exact area by using this expression, the limit of b minus a over n, which is the delta x, times a sigma f of xi n's. And these are all the function values at many x values between a and b. And we add all those times b minus a over n, and then we let n go to infinity. That limit is called the integral. And we symbolize it this way. We use this symbol, which is the stretched s. And it has a subscript and a superscript. The subscript is the left endpoint of the interval over which we're integrating, and the superscript is the right end of that interval. And in the notation, notice that we have f of x times dx. Dx really is the limit representation of delta x. Delta x is specific to what n is, but this dx in the limit, we call it infinitesimal. So this f of x dx, you can think of it like this. Think of an approximation to dx being this, and then f of x, either you use the left endpoint or right endpoint or any point in between. When you evaluate f at this point, somewhere in this subinterval, you get the height times dx. So the height is f of x times dx will give you the area of that tiny rectangle. So this really represents the Riemann sum, and sigma is changed to a stretched s. So this is the definition of what we call integral. And if we know not every limit exists, we know that from the tangent line problem. In this case, if the limit does exist, we say that the function f is integrable on the interval a to b. If it doesn't exist, if the limit doesn't exist, then the function is not integrable on this interval a, b. So in the next video, we ask this question: why do we care about the integrals? Watch the next video.